Assalamualaikum everyone. So let's start from my introduction. I'm Syeda Aiman Mumtaz, currently Women in Tech Lead at GDGOC Comsys Islamabad. So today the topic I've selected is the Visual Language Models, the VLMs, and in the VLMs specifically we're gonna talk about CLIP, and the paper name is Learning Transferable Visual Models from Natural Language Supervision. Okay, before getting into CLIP, let's understand what's VLMs. From the name we can see it's VN and then language models. So what we do that we actually combine the computer VN part and the NLP part, and the combination is the visual language models. And why we do it, we'll study that, and then we'll study that further on. So why VLMs? We see that as humans, we have senses. We have the vision, we have the hearing, and all the senses. So as you use ChatGPT, you use Nano Banana, and all the AIs, right? So it can have the input of the images, the voice, and text input, and then the multimodal. With that multimodal input, and then it can generate multimodal output. It can have multimodals output, right? So it can generate images. Different models have different capabilities. So yeah, so that's after NLP, that NLP to transformer came in, and then there was this, when you pass a lot of data, when you train a lot of a model on a lot of data of sentences, then on the transformer architecture, that the sentence are broken down into the tokens, and then their positional embeddings, and their attention mechanisms, and the model can now just relate the tokens with each other. If a sentence, for example, a cat is sitting on a mat, now the transformer, through transformer and attention, the model knows that the cat and the mat, the first and last sentence, and anything between, they have the relationship, right? So the relationship is learned based on that. The same concept if we apply on the combining the VN and the NLP, that where VLM comes, right? So what we're going to do, that we'll pass the images, the computer vision part, and then we'll pass the related captions of those images, the NLP part, together. And when we do that, what happens is that we can have a lot of we can have predictions and generation, and like a lot of applications that we're going to study next. So okay, so this is the human experience is multimodal, and then the data is also multimodal for the training, right? For the training purpose. Now introducing VLMs. VLMs merge the natural language we already discussed with computer vision, and then they can describe the visual content and answer questions about the images, and then designed to process, integrate both visual and, we already studied this, right? So for example, if after training I just train a model on the images and the related captions, then I can just give an image and then ask questions related to the image, and it can give me an answers. It can understand the image and then data. All right. So the key components and functions of VLMs is the image recognition. You can identify objects in scenes. Now, it's how is it different from CNNs? A short review would be that in CNNs you just have the classification based on the labels, and the labels are just one word, or like one word labels. For example, there is a data of cats and dogs and all that. So you just have just one label, and you, on the classification, the model predicts this, there's a cat or there's a dog in the image, right? But in the VLMs, we don't have just labels or one word labels. We have actual sentences, like the cat is sitting on the mat, the dog is swimming, or anything like that. Okay, so there are whole sentences there that we are going to work on. That's the difference between the normal CNN and then the VLM. So all right, and then object detection, we can actually specify items within the images. We'll study how this works later on. We're just studying the components for now, and then applications. The text generation from the visual input, like I said, we can pass the image, and then you can just ask questions related to the image, and the question answering question. All right. So now let's go to the clip. Now we have learned about the VLMs, that what are VLMs, and then this clip is a type of the VLM we are going to discuss now. Okay, so the clip is the contrastive language image pre-training. The contrastive, basically it's a concept that we'll study in this clip. Okay, so what this clip was built by OpenAI. Okay, so what OpenAI did that it built this model that took the visual concepts and the natural language concepts, Supervision, okay, and through contrastive learning, okay, between and bridging the gap between VN and text. So what does it mean, contrastive learning? This is one of the main feature that clip is based on, and we'll learn in the next slide. So first thing is just the clip is a model and that was trained on a huge amount of data. And when NLP just came in and the more NLP was working and the transformers were there, so with that the vision, combining the vision and the natural language processing came in, right? So in that time the clip was there and we didn't have the data. So what the OpenAI people did was they just collected around 400 pairs from the web. They took the images and their captions, right, and they just built this whole data, huge data, because it was needed to train a model that could actually work. So then they did word that, then they train it. Okay, so how it works, a small introduction would be this, that it has an image encoder, and then it has a text encoder, and then the contrastive loss, okay, and on images and the related data, and then they predict, all right, on the based of the images and text that I can give. Okay, so this is small introduction. The image encoder, what is it, and what the text encoder is. Okay, so you must have studied about in the transformers, that in transformers, okay, in transformers, let me just write it down. Okay, it's very bad because I am not able to control my mouse right now. So anyways, in transformers what happened, that there was a whole sentence and then it got broken down into the tokens, and the tokens were converted into embeddings. What embeddings? Basically the text was converted into a numeric form, the embeddings. There are positional embeddings, and then there's attention mechanism on those. So from a sentence you can just have the transfer to that. We can just like learn the relationship between these, for example, words and this word, and then that's why the GPT or any model can actually even generate the words. How does it know that what would be the next word, what should be this basically the context learning and all that. So it's based on that transformer architecture that it learns the relationship between the words, and it has been trained on large huge amount of data. That's why it can actually predict the text, right? So the encoder concept is that now we're talking about the image encoder. So it's the same, like imagine an image, all right, you pass an image. For example, this is an image of a human, all right. So this image is there, and you know the image is actually pixels in the background. So when I pass this image to a model, and we'll study which model, basically it's ResNet or VIT, the vision transformers, this image is converted into the embeddings, right? It's a feature vector in the end. So we get images encoding, and then with this image we have the data that has a caption related to that image, right? For example, it's a man sitting on a chair, or it's just standing, so there will be a caption related to that man is standing on there. So there will be a whole sentence, right? And that sentence would be encoded, and the embeddings will be done with the sorry, so it will be done with the transformer. All right, so for this there is ResNet. For the image encoding there is ResNet and VIT, VN transformer. And for the text encoder, that there is transformer. All right, and then there's contrastive loss, and yeah, so the training happens just like that. Okay, so let's see next. So we talked about it, that there is image and text encoders, and there are separate neural networks transform the images and text into embedding space. And then there's contrastive objective. What's contrastive? We'll study further on because it's a concept. In short, for now, the contrastive means that what we want is that when we train the model on the image and the related text, the caption, now we want that it should learn how to match the caption with the related image, right? But with that, it should also know that which caption is not related to that image. All right, that's like for example, there's a kid, okay, and you want the kid to know something. For example, that you can just stay in this room. All right, you can just tell the kid that you can stay in this room, and that will be just learning. And if I want to understand the contrastive, you would tell the kid that you can stay in the room and you cannot go outside. You cannot just put something in your mouth, right? Something sharp and all that. And this is contrastive learning, that you just don't tell the model that this image is related to the caption, but you also tell that all the other captions that are not related to this image. All right, so that's how model learns, from the positive and from the negative. All right, that's contrastive for now. And then there's zero shot capability in the clip. What's that? Zero shot means that after the training, all right, so I can just pass an image, and I can just pass this prompts of text. All right, so there could be a dog in the image, an image sitting, dogs just running, and then I can give a prompt that the dog is running or the cat is running, or anything, right? So the model can give the inference, can just predict based on that single prompt. It can learn on that prompt, and then it would know that it's a dog, right, in the image. So that's the zero shot capability. Okay, so after this, let's move to the in depth that how the image and text encoders actually work. Okay, so this is the image encoding. Now I told you that for the image encoders, there is either the ResNet encoder or the VIT encoder. All right. So let's understand it a little bit. Okay, so there could be a ResNet encoder and then the VIT encoders. There are two the variants of the clip model. So let's start from the ResNet. A little introduction, background of what basically ResNet is. Okay. So basically ResNet, the CNN, you have learned in the deep learning that what's CNN. CNN, we just give an image to the CNN, and then the image is there are feature maps all based on those images. All right, and those feature maps through, like, this is an image passed, and based on the image we want to extract the features of the image, right? We want to classify anything. So based on the data on that data, there are feature maps made. This is the okay, there are convolution layers. This is the second convolution layer. Third, the layers basically extract the feature maps. They make the feature maps. All right, and then after that it is passed into a classification, fully connected layers for the classification. Okay, so how is it ResNet? What's different in ResNet from CNN is that ResNet, actually the name came from residual connections. So what happens is that there are a lot of layers between this CNN. All right, it's very deep. So what happens is that when this convolution layer passes the feature maps to the next convolution layer, and then the next one passes it to the next layer, what happens is there's a chance that the feature maps may get distorted. There could be a noise in feature maps, or there could be anything, right? There's a possibility of the problems. So for solving that, what they did in ResNet was that from the previous layer you can pass the input into the, you can skip the connection and then pass it directly to the next layer. So you can think about it that in this way, that just an example, that think about it, if you have certain around for like after 2 hours I'll do something, and then the 2 hours is a big amount of time, right? There's a huge gap, so there's a possibility that you may forget in the middle you might forget it, and you can feel. That's why if you tell your sister or anyone, that you can tell her that just give me reminders after every half an hour, or you can set an alarm for every half an hour. Okay, so that you can remember it, you will not forget it. So that's clear input. Already there will be clarity in it. So something like that, you can understand the concept that if we skip the connection and pass the input directly, so that if this in the middle there is some distortion in the feature maps, the previous layer they pass the data to, all right, to the next layer. So we have the feature maps from this, all right, and then from the previous layer too, from these layers and the previous layers. So that's why this solves a lot of problems, not just this problem, actually there's vanishing gradient problems and all that. So in the deep layers this ResNet works like that, all right. In the clip model, the ResNet encoder works like this, and then there is CNN architecture, convolutional layers, there's a pooling, and then feature vector, and then for final embeddings and L2 normalization, and these are all the deep learning concepts, all right, that you must have already studied. But this was the introduction to ResNet encoder. So this encoders will do what? There will be output of the feature vector, all right, and the ResNet will encode and embed it. The second is the VIT encoders. Now what is VIT? These are the vision transformers. Okay, what they do is, now we have studied about the CNN, that you can pass the whole image, just like this dog image. We pass the whole image and the feature maps are made in the different layers, and then all the work is happening there. The whole image is passed, right? But in the VID encoders, the difference is just that there are patches over the image, all right. So what that means is, for example, there is an image like this of a person. So we won't pass the image directly into the model, like won't pass it here. First, there are the patches are created, like think about it like this. We create patches of the sizes, like okay, we fix it, and then these are the patches. Now this is patch 1, this is patch 2, this is patch 3. We pass these patches here, all right. Like this was an image, we generated the patches patches, and then the patches were passed into the model, all right. So if you're when you're learning this, you'll actually remember the NLP concept, the transformer concept there, that there was a whole sentence, and then the sentence was passed. Before that, it was broken into small tokens, just like that. In VIT, this VM transformers, a similar concept is that the patches are passed, okay, and then they are converted into embeddings, just like text. They're talking about the NLP, and then here they're also positional encodings with patches, multi-heard self-intention, feed-forward neural networks, and then we get in the last we like this a feature vector, all right. So this VIT is just like transformers give us the understanding, because of the attention mechanism, we get the lot better and a more detailed relationship in between the different patches and the feature understanding through VIT encoders, all right. Okay, so this was the VIT encoder, and then there's a patch embedding sequence, and then they are normalized, and we get in the final, just like the this ResNet, we get the embeddings in the VIT encoders, all right. These are just the starting that the model goes through. Okay, so after this, now let's study what happens next. Okay, so after the embeddings, now this is the text encoder, all right. This is the text encoder, and then this is the image encoder that we studied already, right? For example, Pepper the Aussie pup, and then the image of that dog. We just passed it to the embeddings, the transformers, VIT or the transformers. When we pass it just like this is the output feature vector that we get, and from the text we get the same feature vector just like this. Okay, there are a lot of captions, there are a lot of images, we pass it, and then we get this. So you can think of this output, this output is just like a matrix here, right? So what's happening here is what's contrasted learning. We already studied that we don't focus on just the perfect match, but also all on other matches that are not perfect and not actually the matches, right? So okay, you can see this image 1 has an caption or text 1, and then the image 2 has text 2, like that image 3 has text 3. These are the actual matches that were passed, the pairs that were passed, and these are in the diagonal of the matrix. Okay, image 1 text 1, image 2 text 2, image 3 text 3, up to image n text n. But not we are not only focused on just the diagonals. Okay, we actually want to train the model so that it can build a relationship, the similarity score between the image and the related text, right? So this matrix is basically the similarity score. You can think of it like we want this to actually build on the similarity score. So these diagonals, all right, these are the diagonals. We want to maximize the value of these diagonals. We want to maximize, this is what okay, let me just give an overview again. So basically what happens here is, this is text, right? This is the related image, these are the related images. So this matrix is the similarity score that the model will generate, right? So in the diagonal we have all the entries that actually related to each other, so we want to maximize this diagonal entry values. Like for example, there will be 0.6, 0.8, 0.5 and all that. So we want to maximize these, and these other than the diagonal entries are the mismatched ones, right? So this for image 1 there is image text 2 here, for image 1 there text 3 up to n, right? So we want to minimize these values because we want the model to learn that these are not related to the image and this one is the related to that image. All right, okay, so to minimize the other entries that we discussed. Okay, so this is the contrastive pre-training that happens on the data. After that there is the second is from dataset classifier. All right, so what happens is here that you passed all the options, all right, the photo of a object, the plane, car, dog, bird, anything, all right, and then the text encoding happens there, and then there's image encoder, and the maximum similarity one gets the answer, that is the prediction, right? So that's zero shot prediction. This is how the clip works. Okay, so why clip is revolutionary? There are a lot of applications of the clip. All right, so this you can study that we already studied natural language supervision, right? So there's visual representation associated with also the natural language description. All right, and then the zero shot learning, enhanced robustness, and then the clip applications in the real world. So there could be, the applications would be the image search and retrieval. So what can it do is that you can just if the model is trained and it just can do work, that you can pass a caption, it can find the relevant images, all right, from anywhere, because it has already learned that which caption is the best described with images, right? And then there's content moderation, that think about it, that if it already knows that this image has this caption, right? So you can just tell that these words are forbidden, all right, and then if the content has these things, all right, and you define just the words, but it knows the words how they're related to the visual representation. So you can just have the content moderation, and then there could be you can pass an image, and then you can ask questions and anything related to that, right? And then creative tools, all this editing systems, multimodal understanding of the model. So this was all about the clip. All right, and there are other models too. After this there was blip and all that you can actually will study, and you can actually look up into it. There's another thing that I would like you to know, is okay, that is Node LM. Before going, so this is Node LM. If you actually want to read the AI papers, this is a really helpful tool. You just can go here, Node LM, it's of the Google, and just create new notebook, and then just upload any file. Alright, I'm gonna pick any paper, for example ResNet. Okay, so it will generate the summary of the whole paper, right? Just like here I just generated the whole summary, and you can even ask questions here, right? You can ask anything, that what is ResNet, for example. All right, so it will actually answer you related to the document. And okay, so and you can even generate video feedback, inquiries of flashcards or slide desk. It actually generated the slides before too, and the slides are actually quite easy to understand. Okay, so see, it has given all the answers. Now how is this better than ChatGPT or any other model? You can learn from there too, no problem. But the thing is that this is actually helpful for the research area. You just have to pass this, and just let me generate the slides and I'll show you. And actually I've generated before the slide. I'll show you the clip slides that I've generated from there. So this was the paper that I passed into it, and these were the slides that it generated. You see that a summary that it generated: a revolutionary computer vision system developed by OpenAI that learns directly from natural language supervision rather than restricted hand level categories, by training on the 400 image text pair sourced on the internet. Embedding spaces, the visual concepts are related to raw text, and the zero shot transfer model to perform diverse object recognition, action recognition without requiring additional training data. Claim more robust. Okay, all right, so see, all this is written, the whole summary of the paper, and these are the slides. See how pretty they are. So this is the okay, this was something that we actually skipped, but this is about that in CNNs we had like limited classes. For example, there were 1,000 classes. Okay, so the model will just guess those 1,000 classes, nothing else, right? It will just learn this. And if you want it to actually recognize some other classes too, we have to train it from the scratch again. Okay, so NLP, okay, like NLP that we don't have to train the model from scratch for everything, right? We just pass the whole data and it just has learned all these things. So we, for the same concept in the computer vision, that's the clip model, you don't have to train for like from scratch from everything. It has the NLP sentences, long sentences, scenarios that it can relate to the image. The image can have, not like for example, a dog is standing on the table. Now there's standing, the dog standing there, right? So the whole image is learned. Not just the dog. There is dog and there is wall and all the in the sentence. They all things are learned in those. Okay. And there's this, we already saw that 400 million data, and then there's the best one to learn from this was contrastive clip, and we had to maximize this. See, we have to maximize the diagonal entries and have to minimize the other entries. See, the core idea was this, so that we learn which caption is best for which image. And then zero shot prediction. The pre-trained model can perform new classifications without additional training. So on the go, you can just give the image and then all the text prompts. It will learn and calculate similarity, and then you just on the fly you can just give it new prompts that okay, so it will learn it. And then zero shot clip, it has 76% accuracy, more accuracy. And then you can see all this comparison that from the paper it is okay visualized. The clip wins in these areas. The clip was the winner, and for highly specialized abstract tasks, clip struggles. Okay, zero shot. Okay, you can just see these where it when in all this. So clip VIT, clip ResNet. Clip VIT is performance C. It's more score is better than ResNet one, because VIT actually learns on the patches, so it has more in-depth learning. And then yeah, so you can just see all this. So this is Note LM. You can just get these slides and all that. Okay, so So yeah, that was the end for today that we learned in the clip model.